2017 Canadian Open Mathematics Challenge, Part C. For a positive integer n, we define the function p at n to be the sum of the digits of n plus the number of digits of n. For example, p45 would be 4 plus 5 plus 2, which is 11. Note that the first digit of n, reading from left to right, cannot be 0. Determine P2017. So let's apply the same principle. P2017 would be the sum of the digits, so that's 2 plus 0 plus 1 plus 7 plus the number of digits of n. So in this case, the number of digits is 4. So there we go. So that looks like 3, 10, 14. So P2017 is 14. Part B, determine all numbers n such that p at n is 4. All right, so we got to play around with this a little bit. So p at n, they want to be 4. Okay, so I think what we have to do is look at this from the perspective of how many digits does it have. So number of digits, so if it has one digit, then what's the scenario? Well, that means p at n is 4 and it has one digit. So that's going to be just n plus 1, right? Because n is the sum of the digits, and then 1 is how many digits there were. And that's got to be 4. So that means n is 3. And I think that's it. So I'll keep a tally here. N can be 3 of our values. Okay. So now we did that one digit. Now let's try two digits. And let's say n in this case is a number like it's a, b, so like 54. So the sum of the digits would be 5 plus 4, and then you have to add 2 because there's two digits. So that means p at n would basically be p at ab, which is the sum of the digits a plus b plus 2. Correct? And they're saying that is equal to 4, because p at n is 4. Okay, so a plus b plus 2 is 4, so that means a plus b is equal to 2. So we have to come up with scenario that a plus b is 2. Well, using integers, well, you can have 1 and 1, or you can have 2 and 0. You can't have 0 and 2 because that would no longer be a two-digit number. 0 and 2 is 2, which is a one-digit number. So that's not possible. So only those two. So that means n is either 11 or 20. Okay, so we got n equal 11 and n equal 20. All right, and let's see, 3 digits. Let's see what happens here. 3 digits, okay. So this time my n is like an a, b, c. So the sum of the digits would be a plus b plus c. But then you'd also have to add 3 because there's 3 digits. That would be sort of how do you calculate p of n. So p of n, which is essentially the same as p at a, b, c, is a plus b plus c plus 3. And they're saying that is equal to 4. So that means a plus b plus c is equal to 1. So what are my scenarios? I think the only one is just 1, 0, 0, because you can't have 0 as a because that would no longer make a 3-digit number, right? So that means n, the only possibility here is 100. So here we go. And I think once you have 4 digits, it falls apart, because then a plus b plus c plus d plus 4 would be equal to 4. So that means a plus b plus c plus d would have to equal 0, and that's not possible. The only way it's possible if all of them are 0, but that's not going to make a 4-digit number, or if you have some negatives, but you can't have negatives because they have to be positive digits. So that's it. So these are the only 4. N equals 3, 11, 20, and 100. Part C, determine with explanation whether there exists a number n for which p at n minus p at n plus 1 is greater than 50. So p at n minus p at n plus 1 greater than 50. So by definition, this is n plus 1. And then minus, this is n plus 1 plus 1. Yeah, and that's got to be greater than 50. Okay, so there's a number n. All right, but this is really just if n has one digit, because this becomes -1 is greater than 50, which obviously makes no sense. So that means obviously that n has to have more than one digit. N has to have several digits, actually. Okay, so after some experimentation, we can conclude that if it changes the number of digits, when you go from n to n plus 1, if the number of digits changes, then we have a pretty good chance of getting over 50. So for example, like 99 to 100. If n was 99, n plus 1 would be 100. This is 2 digits. This is 3 digits. If the number of digits changes, then we have a good chance. So let's try it. What happens? Let's try this with 99. P99 minus P100. Let's see what happens. So this would be 9 plus 9 plus 2. And then this is going to be 1 plus 0 plus 0 plus 3. So that's going to be what? 20 minus 4, which is 16. And 16 is not greater than 50. Okay, that's fine, but I think we're headed in the right direction here. Let's keep going. Shouldn't take us that long. Let's try the next one. 999 minus P1000. This is going to be 3 times 9 plus 3. And this is 1 plus 4. So that's what? 30 minus 5, which is 25. Okay, 25 is not greater than 50, but we are getting higher. So if we're getting higher, that's good. Let's keep going here. Eventually, we'll be able to get up to 50, I believe, or greater than 50. So the next one, P9999 minus P10,000. So that's going to be 4 times 9 plus 4. And then this is 1 plus 5 this time. So that's 40. 40 minus 6, which is 34. Okay, it's not greater than 50, but you notice we are getting higher. So eventually I think we'll be able to reach 50. Let's try the next one. P999999, 5 nines this time, and this will be P100,000. So that's 9 times 5 plus 5 minus 1 plus 6. So that's 50 minus 7, which is 43. Okay, getting higher. And next one, so P this time 6 nines this time, and P 1,000,000. 1, 2, 3, 4, 5, 6. Okay, so that's 6 times 9 plus 6 minus 1 plus 7. So 6 times 9, 54 plus 6, 60. 60 minus 8, and that is 52. There you go, greater than 50. And what do they want? There exists a number n. Yeah, we just showed it. And our number n was this guy right here. This is our n, 999999. And I mean, there's many, I don't know. Yeah, there should be several, right? That would satisfy this. And they just want you to show one, whether there exists an n for which that is satisfied, and it does. And I'm pretty confident that there'd be more than one such number. And if you found that, that would be fine, as long as you explained your methodology of finding it. A function f at x is periodic with period t greater than 0 if f at x plus t is equal to f at x for all x. The smallest such number t is called the least period. For example, the functions sine x and cos x are periodic with at least period 2 pi. Let a function g at x be periodic with the least period t equal to pi. Determine the least period of g of x over 3. All right, well, I will use a graph because I think graphs are helpful. So let's say I have g at x, and it has a period of pi. So, let's draw it first. I like how they gave these examples because it kind of makes me think, well, I'll just stick with those. I'll just stick with sine and cosine. Might as well. So if the period is pi, that means it's got to go through one full cycle by pi on the x-axis. And that is the graph of sine of 2x. Because the sine of x has a period of 2 pi, and they even told you that in the question as an example. Okay, so this works. This is an example of a function that has the period of pi. So we want the period of g at x over 3. Okay, so substituting that, that's going to be the sine of 2x over 3. Okay, so we graph this, and with a few points, you can graph this one full cycle, and that would give you 3 pi over 2 and 3 pi. So one full cycle would be by the time you get to 3 pi on the x-axis. So here the period, or the least period, is 3 pi. And that's it, really, for part A. Part B. Part B says, determine the least period of h at x, which is sine of 8x plus cos of 4x. Okay, so we have the sine of 8x, which is the sine of 8x plus 2 pi, right? Because the graph has a least period of 2 pi, and then we can factor out the 8, and that would give me x plus pi over 4, like that. And therefore this is a least period of pi over 4. And then in a very similar way, we do the same thing for cos of 4x. That's cos of 4x plus 2 pi, because the period of cos of x, of 4x, can be 2 pi. Not necessarily the least period, but a period. And then if you factor out the 4, you will get x plus pi over 2. And therefore the least period is going to be pi over 2, because they're asking for a least period. Okay, so I guess the period of the sum, which is sine of 8x plus cos of 4x, that is the least common multiple of the two periods. So least common multiple of the two periods. So in this case, the two periods are pi over 4 and pi over 2. So the least common multiple of those two is pi over 2. So that would be the least period of that sum. Determine the least periods of g at x is equal to sine of cos x, and f at x is equal to cos of sine x. All right. So we have, again, g at x plus 2 pi that's a period, is the same as sine of cos of x plus 2 pi. Right, because cos of x has actually a least period of 2 pi. And using trig identities, well, this one is just cos of x. And then this one looks to me like it's the same as g at x. Yeah. So therefore, the period here is 2 pi. Since we were able to prove that this is equal to that. And then for the next one, we're going to have to use some trig identities. So trig trigonometry identities. Fortunately, they're not the more difficult ones. So f at x, but I'm going to use pi this time. That's what's going to make it work. And then substitute it. It's the cos of sine of x plus pi, if we make that substitution. And now this is where the trig identities come in. This part in here is the same as minus sine x. Yeah. And then cos, again, minus sine x is the same as sine x. And then this part is just f at x. So this period is pi. And yeah, that's what they wanted you to find individually. What is the least period there and what is the least period there? Let x, y, and z be an acute angle triangle. Let S be the side length of the square which has two adjacent vertices on side yz. One vertex on side xy and one vertex on side xz. Let h be the distance from x to the side yz, and let b the distance from y to z. If the coordinates vertices have coordinates 2, 4, 0, 0, and 4, 0, find b, h, and s. Okay, so let's label this. First, what I want to do is draw one line from the top to the bottom. So from x down like that. And that will, I think everything will be labeled. So the side of the square is s. So that's pretty good. And then we got to put this on a coordinate axis. So let me draw in a coordinate axis. And I can start labeling. Z was what? 4, 0. So this is 4 on the x-axis. And then y was just 0, 0. So that's just the origin. X was 2, 4. So this is 2. And this is 4 up here. And what else? I think that's it, right? And then this part in here, the top to bottom, I will call h. And then therefore this part in here, just that part, is h minus s, right? Because this is perpendicular and this is perpendicular. Okay, I think that's pretty decent. And now with similar triangles, or we can get that h minus s over s. So this altitude over that base is the same as this altitude over that base. So that's going to be h over b. Well, where b is the distance from y to z. Okay, well, some of this they already gave us. They gave us that z is 4, 0, so b immediately we figure out is 4. And then h, based on the fact that x is 2, 4, h is 4. And what else? And then the other one is s. How do we get s? Oh, s, we have to use this formula here. Okay, no problem. So that's going to be 4 minus s over s is 4 over 4. So 4 minus s over s is 1. So 4 minus s is s, and therefore 4 is equal to 2s, and therefore s is equal to 2. So h is 4, b is 4, and s is 2. Part B, given the height is h equals 3, s equals 2, find b. So I think we will just use the same formula that we did previously, discover, through similar triangles, and that's h over s. H minus s over s is h over b. So h they've already given us is 3, s is 2, and therefore we just easily can solve for b. So this is 1 over 2 is 3 over b. Cross multiply and you get b is equal to 6. Part C, if the area of the square is 2017, determine the minimum area of the triangle XYZ. So we had labeled the square as having side s, so they're saying that s squared is equal to 2017, right? The area of the square. Okay, so what we have to do is manipulate this formula and make it in terms of s. So s equals something, because this says that s squared equals 2017. So I think I can do that. I can bring this over. So I've got h minus s over s is h over b. First, let me bring this h down into the denominator and the s in the numerator by cross multiplying like that. This breaks up into h over h minus s over h, and this is s over b. This is 1, and bring the s over h over like that. And now get a common denominator, h, h, b, b. So that's going to be hs plus sb over hb. Okay. And I think I can bring the hb, and then I'll factor out the s, h plus b, and therefore s is hb over h plus b. So exactly what I wanted. I wanted a equation in terms of s, and I have it. So since now I have s is equal to hb over h plus b, I can say that s squared, because it's equal to 2017, that hb over h plus b all squared is equal to 2017, like that. So that means that this is h squared b squared h plus b all squared is equal to 2017. Now the area of that triangle XYZ is 1/2 base times height. Now the base is b and the height I have called h. So if I just call the area A, that's A is equal to 1/2 base times height. Or you can write base times height is equal to 2a, whatever. Okay, so now this is where we have to use something called AMGM. AMGM, some of you know, some of you don't know. It's arithmetic mean, geometric mean. It's a inequality, arithmetic mean, geometric mean. And it states that if you take the arithmetic mean of two numbers, so a plus b divided by 2, it will be greater than or equal to the geometric mean, which is a times b under the square root sign. And you can, manipulate this in its own way. For example, if you were to square both sides, this would become ab squared over 4 is greater than or equal to ab. And you can put everything on one side, and it would be 1/4 is greater than or equal to ab over a plus b all squared, like that. Now the good news there is that that looks, in my opinion, similar to this, right? Because if you take that and kind of write it in a different way, which is put this hb out front and then just have hb and then the h plus b squared, then you'll see that this part is the same as that part, or it looks identical, it's just the letters are different. And that is equal to 2017. And then let's isolate this part and put the hb in the denominator. And based on the AMGM equality, we know that that is going to be less than 1/4. So this is less than 1/4, and therefore this is less than 1/4 since those are equal. So that means that if you were to just look at that part, 2017 over HB is less than or equal to 1/4. So cross multiplying, you'd get 2017 is less than or equal to HB over 4. And if I break this up into 1/2 1/2 HB, like that, this represents the area. Right here, see? 1/2 B times H is the area. So I'll just call that A. So 1/2 A is 2017. So that means that A, if you multiply, is 4034. A is greater than or equal to 4034. So therefore, the minimum area is 4034. It can be greater than that, but the minimum is 4034. Let n be a positive integer, and Sn is the set 1, 2, ... until 2n minus 1, 2n. A perfect pairing of Sn is defined to be a partitioning of the 2n numbers into n pairs, such that the sum of the two numbers in each pair is a perfect square. For example, if n is 4, then a perfect pairing of S4 is 1, 8, 2, 7, 3, 6, 4, 5. It is not necessary for each pair to sum to the same perfect square. Show that S8 has at least one perfect pairing. Okay, so by definition, S8 would be the set of 1, 2, 3, 4, all the way up until 2n. So 2n in this case would be, if n is 8, 2n would be 16. So we're going all the way up to 16. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So what we have to do is we have to arrange these 16 integers into pairs. So somehow there's going to be how many pairs? 8 pairs. So, okay. And then the goal of each of these 8 pairs is that the sum of the two numbers in the pair is a perfect square. All right. So I guess we just have to experiment. Let's see. Well, first of all, what perfect squares are candidates? We can't use 1 because the smallest sum is 1 plus 2, which is 3. So immediately that exceeds 1. But we can use 4. 4 could be a possible perfect square. 9, 16, 25, and I think that's it, because 36 we won't be able to get because the largest sum is 31. All right, so these are my candidates. Let's see what I can get here. Oh boy. Well, let's see. 1 and 8. That takes care of 1 and 8. That's a 9. 2 and 7. That takes care of those guys. 3 and 6. That's 9. 4 and 5. That's 9. And I think we've exhausted the 9s. And then the remaining numbers have to add up to a perfect square. So 9 and 16, that is 25. That's a perfect square. Yeah, I think I can do it. And then 10 and 15. Yeah, 10 and 15. And then 11 and 14. Yeah, and then 12 and 13. Great. Okay, so this is one such example of a perfect pairing. All right, great. So part B. Show that S5 does not have any perfect pairings. So S5, by definition, would be the digits from 1 to 10. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it does not have, okay, same as before, what are my candidates for perfect squares? I can't use 1 because the smallest sum is 3. So 4 I could probably make, 9 I can make, and 16 I can make, but then that's it because the biggest sum is 19, so I can't make a 25. Okay. So I've got to make 5 pairs, right? So 1, 2, 3, 4, and 5 pairs. And each has to be a perfect square. And they're showing us, they're saying that we can't do this. Show that it can't be done. All right. So first, let's just start by eliminating some of these. Let's make a 16. I think I can make a 16 pretty quickly. 6 and a 10. So that will take care of the 6 and the 10. So I'm using 16. And then And then if I want to make a 16 again, I've got to use, I don't think I can make a 16 again. 9 and 8 is the largest, which is, well, I can. 7 and 9 is 16. So I can make a 16 again. So some possibilities still exist. I'm going to try to make another perfect square with 3. And if I make a 3, I can use 3 and, well, there's no 13 obviously, but how about 3 and 6? But 6 is already taken, so I can't use 3 and 6. So I would have to have no choice but to put a 1 in there, and that would make a 4. Okay. Now, if I put this 8 here, then how can I make a perfect square? Well, I need a 1 to make a 9, but the 1's already taken. And I would need an 8 to make a 16. And the 8 I can't because I already have the 8 here. I can't use 8 twice. So here there's no option here. No option. So we're stuck. So since there's no option, I hope this shows that S5 does not have any perfect pairings.